You are wearing a quantum physics experiment right now. 2 tiny plastic shells sitting in your ears, each one weighing less than 5 grams. People think they are simple speakers. Plug in, play music, go home. But those earbuds are running at least 7 tricks that physicists spent most of the 20th century trying to understand. Tricks that only became possible because electrons, particles so small that billions of them could sit on the period at the end of this sentence, do things that make absolutely no sense in the normal world. They walk through walls. They exist in 2 places at once. They carry forces using particles that appear for a fraction of a second and then vanish. 7 tricks. All of them happening right now, inside the devices you bought at the mall. Some of them were discovered by people who had no idea a device like this would ever exist. Some of them were considered purely theoretical until engineers had no choice but to use them. Every single one of them is real, documented and verified by sources that carry more weight than you might expect from a story about wireless earbuds. Let us go through them one at a time. If you value documented science history like this, subscribe. It is the best way to support our work. Also, drop a comment with what city you are watching from. This script draws from peer-reviewed research published in the journal Science in 2025, proceedings from the IEEE International Electron Devices, meeting going back to 1988, Nature Nanotechnology from 2024, and the foundational work of Nobel Prize-winning physicists, including Leo Esaki, Richard Feynman, Julian Schwinger, and Shinichiro Tominaga. Now back to the information. Number 1. Quantum tunneling in flash memory, first described mathematically in 1928, first proven in silicon in 1967, and working inside your earbuds right this second. Your earbuds hold settings, your paired device list, your saved equalizer profile, your noise cancellation preferences, maybe your firmware version. All of that data lives in a tiny chip inside the earbud called flash memory. It is the same type of memory found in your phone, in solid-state hard drives, in USB sticks. And every single bit of data inside it, every 1 and every 0 exists because electrons did something that classical physics says is flat out impossible. Here's what flash memory actually is. Inside the chip, there are millions of tiny switches called transistors. Each transistor has a special structure built into it, sandwiched between layers of silicon dioxide glass, essentially transparent, extremely thin glass. There's a little metal cage called the floating gate. That glass is the wall. Electrons need to get in and out of the floating gate cage for the memory to store data, but the glass is in the way. In a normal world, the world of billiard balls and car engines and everything you can see with your naked eye, a particle either has enough energy to get over a wall or it does not. If it does not, it turns around. Full stop. But electrons are not billiard balls. Electrons are quantum particles. At the scale of nanometers, they behave like waves. And waves do not simply stop at a wall, they fade through it. Think of a sound wave reaching a thin wall. Most of it reflects back, but a little bit makes it through. The wave of an electron reaches the glass wall, and on the other side, there is still a tiny amount of wave left. That is not a metaphor. That tiny remaining wave represents a real measurable probability that the electron actually exists on the other side. If the glass layer is thin enough, somewhere around 10 nanometers or less, which is roughly 100 times smaller than a red blood cell, that probability becomes significant. Electrons appear on the other side of a wall they should never have been able to cross. This is called quantum tunneling. 2 physicists named Ralph Fowler and Lothar Nordheim worked out the mathematics of it in 1928 at Cambridge, England. They were studying a completely different problem, why electrons escape from metal surfaces under intense electric fields, but the equations they wrote described something that would later become the foundation of every flash memory chip on Earth. Their names are still attached to the effect. It is called Fowler-Nordheim tunneling. In 1967, 2 engineers named D. Kong and S.M. Tseng at Bell Labs in New Jersey published a paper titled A Floating Gate and Its Application to Memory Devices. That paper explicitly used the Fowler-Nordheim tunneling equation. It was the first documented description of how quantum tunneling could store information in a silicon device. The idea grew slowly at first. Then, Eli Harari, working at Hughes Microelectronics in Newport Beach, California between 1976 and 1978, proved that thin silicon dioxide films of around 100 angstroms, that is 10 nanometers, enabled efficient and reliable electron conduction for both writing and erasing memory. His paper in the Journal of Applied Physics, published in 1978, demonstrated the system was manufacturable, reliable, and had high durability. More than 20 years after Kong and Sei, Toshiba took the floating gate concept and invented NAND flash. Their first NAND flash paper was presented at the IEEE International Electron Devices meeting in 1987, held in San Francisco. The following year, 1988, Toshiba commercially launched the technology. Their design used Fowler-Nordheim tunneling for both writing data into the floating gate and erasing data out. The memory cell was small, efficient, and enormously scalable. Between 1988 and 2016, the NAND flash cell shrank by more than 10,000 times. Every generation smaller made the tunneling more effective because the oxide wall got thinner. More tunneling, more efficient writes and erases. Today, the oxide layer in modern NAND flash is around 10 nanometers thick. Modern earbuds store settings in chips descended directly from that 1987 Toshiba design. The floating gate, accessed by electrons that break the rules of classical physics every time you save a preference, is the reason you do not have to repair your earbuds every morning. Every song you skip, every call you answer, every volume adjustment, recorded by electrons walking through glass, cold, glass, gone. Number 2, quantum confinement inside the processor chip, a phenomenon that became practically unavoidable once chip features crossed below 7 nanometers, which happened in mass-market consumer devices around 2017 and 2018. Your earbuds have a processor. The Apple H series chips inside AirPods Pro and the Qualcomm QCC series, chips inside earbuds from Sony, Samsung, and dozens of other major manufacturers handle the Bluetooth signal processing, the noise cancellation algorithm, the battery management system, and the audio codec decoding. All of that computation happens inside a chip smaller than a grain of sand, running transistors measured in single-digit nanometers. At that scale, something unavoidable starts happening to the electrons inside the chip. They stop behaving like they have room to move freely. They start behaving like they are trapped in a very small box. This is quantum confinement. When you force a quantum particle into a very small space, and we are talking spaces only a few nanometers across, the particle cannot hold just any amount of energy. It can only occupy specific allowed energy levels. There are forbidden gaps between them, no in-between states. In the language of physics, the energy becomes quantized. Quantized means it only comes in distinct chunks, like the rungs of a ladder instead of the smooth slope of a ramp. This word quantized is actually where the word quantum comes from. Instead of a smooth, continuous range of possible energies, the electron can only jump from one fixed level to the next. Nothing between rungs is allowed. In chips from the 1980s and 1990s, transistors were tens of micrometers across. The electrons inside had plenty of space. Quantum confinement barely mattered. Classical physics described the chip's behavior well enough to design around. But as transistors crossed the 10 nanometer mark, the quantum effects became impossible to ignore. A principal engineer at Applied Materials stated publicly around 2018 that when transistor body dimensions shrink very small, the semiconductor band structure gets quantized, meaning only discrete energy levels are allowed for the electrons inside. This changes the threshold voltage of each transistor, the exact amount of voltage needed to switch it on or off, in ways that classical models simply cannot predict. Engineers designing chips below 7 nanometers now routinely use quantum mechanical computer simulations to model their transistors. Classical design tools fail. You cannot predict how the chip will behave without treating electrons as waves confined in small spaces. Samsung unveiled gate-all-around transistors starting at 3 nanometers using nanosheet structures around 2021. The gate-all-around architecture wraps the transistor's controlling gate entirely around the conducting channel, giving engineers much tighter control over the quantum-confined electrons inside. A 20% improvement in power and performance per generation was the target. The chip inside your earbud was designed with quantum mechanics built into the foundational math. Every time you press play, quantum confinement is shaping how the switches inside that chip open and close. Number 3, quantum tunneling leakage, the uninvited quantum effect that would drain your battery in minutes without a specific engineering solution discovered in the early 2000s. This one is not glamorous. But it is real. It is happening constantly inside your earbuds, and the battle against it determines whether your earbuds last 6 hours or 6 minutes on a charge. When a transistor is supposed to be off, when no current signal is passing through, electrons still leak. They tunnel through the gate oxide barrier even when they are not supposed to be there. This is called gate leakage or leakage current. It wastes power continuously and generates heat. At large transistor sizes, the gate oxide is thick enough that tunneling probability is negligible. You can ignore it in your calculations. But as transistors shrank below 100 nanometers in the early 2000s, engineers at IBM and Intel began documenting unexpected electrical behavior. Current flowing through transistors that were clearly switched off. By 5 nanometers and below, if the insulating barrier inside a transistor gets thinner than roughly 1 nanometer, tunneling current flows freely even when the device is in its off state. The transistor no longer holds its off state reliably. Logic operations fail, data corrupts, power drains continuously for no useful purpose. The solution came from material science. Engineers replaced silicon dioxide, the traditional gate insulator, with hafnium-based oxide compounds. Hafnium oxide has a higher dielectric constant than silicon dioxide. In plain language, hafnium oxide can create the same electrical insulating effect with a physically thicker layer. A thicker layer means a wider quantum wall. A wider quantum wall means the tunneling probability drops dramatically, because quantum tunneling probability falls exponentially as the barrier gets wider. Intel adopted hafnium-based gate dielectrics in its 45 nanometer chip generation around 2007. The rest of the industry followed. A European research collaboration demonstrated field effect transistors controlled via quantum tunneling rather than the usual thermal injection mechanism, showing that this quantum approach could reduce gate voltage from roughly 1 volt down to 0.2 volts, cutting power consumption by up to 100 times in those experimental devices. The research illustrated how quantum tunneling, properly engineered, could be a feature rather than a bug. Your earbuds give you 6 hours of battery life on a single charge. Without hafnium oxide and careful quantum leakage management, that number would be destroyed. The battle against uninvited quantum tunneling is one of the central engineering challenges of modern chip design, and it is happening inside the earbuds you use every day without a second thought. Number 4, wave-particle duality in the Bluetooth signal, the quantum nature of the 2.4 gigahertz electromagnetic wave carrying your music invisibly through the air. Your phone sends music to your earbuds wirelessly. The Bluetooth signal travels as electromagnetic waves at 2.4 gigahertz. That means 2.4 billion complete wave cycles per second cross the air between your phone and the earbuds in your ears. The earbud receives that wave, decodes it, and turns it into sound. It sounds like engineering. It is also quantum physics at its most foundational. The wave is made of particles called photons, and each photon carries a fixed, quantized amount of energy that cannot be divided. This is wave-particle duality. Electromagnetic radiation, light, radio waves, microwaves, Bluetooth signals, X-rays, gamma rays, all of it is simultaneously a wave that spreads through space in a stream of discrete particles that arrive one at a time. These two descriptions sound contradictory. They are not. They are two different ways of describing the same quantum reality. The mathematical connection between the wave and the particle was worked out in large part by Albert Einstein in 1905. Einstein showed that the energy of a single photon equals Planck's constant, a tiny fixed number, 6.6 times 10 to the negative 34th joule seconds, multiplied by the frequency of the wave. A 2.4 gigahertz Bluetooth photon carries exactly Planck's constant times 2.4 billion hertz of energy. That is a fixed, unbreakable number. You cannot receive half of that photon. You cannot receive 1 1/3 of that photon. The energy arrives whole in one packet, or it does not arrive at all. Einstein won the Nobel Prize in Physics in 1921, partly for this discovery. At the time, many physicists did not believe him. Today, it is one of the most experimentally confirmed facts in all of science. The antenna inside your earbud is a tiny strip of metal, typically less than 30 millimeters long, tuned to resonate at exactly 2.4 gigahertz. When photons from your phone's Bluetooth transmitter strike this antenna, they cause electrons in the metal to oscillate. Those oscillating electrons produce an electrical signal that flows into the Bluetooth chip inside the earbud. The chip processes that signal, extracts the encoded audio data, and routes it to the audio processor for decoding. The entire chain, photon absorbed by antenna, electron excited, signal converted, audio decoded, music played, is a quantum mechanical process repeated billions of times per second. To avoid interference from Wi-Fi networks and microwave ovens, which also operate on the 2.4 gigahertz band, Bluetooth uses a technique called frequency hopping spread spectrum. The connection hops between 79 separate frequency channels at up to 1,600 hops per second. Each hop shifts the frequency of the signal. A shift in frequency means a shift in the energy of each photon being transmitted. The earbuds and your phone stay synchronized, tracking each other across channel changes many times per second. You hear no interruption. The quantum bookkeeping happens silently and continuously. Number 5, quantum mechanics in the battery's charging process, documented experimentally in the journal Science in 2025, and a second older quantum effect silently shortening your battery life over hundreds of charge cycles. The small lithium-ion battery inside each earbud stores power that runs the Bluetooth chip, the noise cancellation processor, and the audio driver. When you place the earbuds in their charging case, lithium ions travel across the boundary between the anode and the electrolyte, moving from one electrode to the other and storing electrochemical energy. For decades, this process was understood as classical chemistry. Move the ions, store the energy, discharge it later, nothing quantum required. In 2025, a paper published in the journal Science, with commentary from Robert E. Warburton titled Battery Charging Goes Quantum, presented experimental evidence that lithium-ion battery charge and discharge occur through a coupled ion-electron transfer mechanism at the electrode-electrolyte interface. This mechanism cannot be fully described by classical chemistry alone. The quantum mechanical behavior of electrons at that interface governs the rate at which the battery charges. The exact process underlying how lithium ions insert into the electrode material, and therefore how quickly your earbuds recharge in the case, is a quantum mechanical event. This was not theoretical prediction, it was laboratory measurement. But there is a second and older quantum effect working inside your earbud battery. It has been studied for years. It is called quantum tunneling through the solid electrolyte interface. When a lithium-ion battery is first charged, a thin protective layer forms naturally on the anode surface. This layer is called the solid electrolyte interface, abbreviated SEI. Its job is to act as a blocking barrier. It is supposed to stop electrons from leaking into the electrolyte and triggering destructive side reactions that would break down the battery chemistry. In classical physics, no electron could cross this barrier. The energy required to cross it is too high. But electrons are quantum particles. They tunnel through the SEI anyway, one at a time, cycle after cycle, not in enormous numbers on any single charge, but consistently. Researcher Dr. Emmanuel Peled, who made major contributions to understanding this interface, proposed using subnanometer insulating coatings on the anode as a way to suppress this tunneling. The math behind the required barrier thickness involves the tunneling probability falling exponentially with distance, expressed in the literature as e to the power of -40 at the critical thickness limit, a number so astronomically small it is functionally zero. When your earbuds lose battery life after 300 or 400 charge cycles, when the 6 hours of playtime becomes 4.5 hours, quantum tunneling through the solid electrolyte interface is part of the reason. Slow, invisible, cumulative, every charge cycle, every night sitting in the case, the quantum debt adds up over time. Subscribe if you want more documented science history like this. Drop your city in the comments. Back to the story. Number 6. Destructive interference and the physics of silence. A wave mechanic that makes noise cancellation possible, running in real time on a chip small enough to fit inside your ear. Your noise-canceling earbuds do something that sounds impossible when you describe it out loud. They listen to the noise around you. They generate a new sound, a mathematically precise, perfectly inverted copy of that noise, and play it into your ear at the exact moment the original noise arrives. Peak meets trough, compression meets rarefaction. The two waves collide inside your ear canal and cancel each other out. What you hear is silence where there was noise. This effect is called destructive interference. Destructive interference is a fundamental property of waves, not just sound waves, but all waves. It is described by wave mechanics, which is itself part of the quantum mechanical framework. The concept was known to physicists long before anyone thought about wireless earbuds. A German physicist named Paul Leweg filed a patent in 1933 describing the core idea: generate an inverted sound wave to cancel an incoming noise wave. The patent was technically visionary and practically useless for decades. The core problem was speed. To cancel a sound wave effectively, the counter wave must be generated and delivered before the original wave finishes entering the ear canal. Sound travels at roughly 340 meters per second. At that speed, the window for intervention inside a small ear canal is measured in microseconds. Analog electronic circuits of the 1930s could not compute fast enough to hit that window reliably. The Bose Corporation spent nearly a decade developing a practical noise cancellation system in the 1980s. Their original goal was not consumer music listening. It was pilot headsets for military and commercial aviation, where engine noise causes permanent hearing damage and makes cockpit communication dangerously difficult at altitude. The first commercially viable Bose noise-canceling headset was designed for aviation cockpits. For years, the technology remained large, expensive, and tethered to a power supply. It could not fit inside a small earbud. What changed was the arrival of digital signal processor chips, DSP chips, built from transistors designed to quantum mechanical specifications. A DSP chip running active noise cancellation inside your earbud performs the following complete sequence in under 1 millisecond. External microphones mounted on the outside of the earbud capture the incoming ambient sound around you. The DSP analyzes the captured sound wave, identifying its dominant frequencies in hertz and its amplitude in decibels. The chip generates a perfectly inverted copy of that wave, the anti-noise signal. The anti-noise signal fires through the earbud driver into your ear canal at the exact moment the original noise arrives from outside. The two waves meet inside your ear. They cancel. You hear quiet. Modern noise cancellation systems from companies like Qualcomm, whose audio chips power earbuds from Sony, Samsung, and many other brands, run adaptive algorithms that continuously adjust. They track how tightly the earbud sits in your ear canal, because a loose fit changes the acoustic environment and reduces cancellation efficiency. They track real-time changes in the noise level around you. They recalculate hundreds of times per second. None of this was possible before chip technology built on quantum mechanical design principles made processors small enough, fast enough, and low power enough to fit inside a device weighing less than 5 grams. The path from Leweg's 1933 patent to the earbuds in your ears runs directly through the quantum mechanics of transistor design. The earbuds listen, the chip calculates, the wave disappears. dozens of times every second, while you do nothing. Number 7. Quantum electrodynamics. Inside the speaker driver, the deepest and most precisely confirmed theory in physics, describing exactly why any of this produces sound at all. You hear music because a small component inside your earbud called a driver moves back and forth very fast. The driver is a miniature speaker. It contains a coil of wire wound many times into a small cylinder, a permanent magnet, and a thin membrane called a diaphragm. When the electrical audio signal passes through the coil becomes an electromagnet. The permanent magnet in the earbud housing either attracts or repels the coil depending on the direction of the electrical current. The coil moves in or out. The diaphragm, physically attached to the coil, moves with it. The moving diaphragm pushes and pulls the air inside your ear canal. Those air pressure changes, compressions and rarefactions, traveling outward from the diaphragm, are sound waves. Those sound waves vibrate your eardrum. Your brain translates the vibrations into music. A typical earbud dynamic driver diaphragm measures between 6 millimeters and 15 millimeters in diameter. Consumer earbuds commonly use drivers in the 8 millimeter range. The diaphragm moves back and forth between 20 hertz and 20,000 hertz, the full range of human hearing, reproducing the thump of bass as readily as the shimmer of high frequencies. 20,000 complete mechanical cycles per second. At the top of the range, each one driven by electromagnetism. Here's where quantum physics enters. Why does passing electric current through a coil create a magnetic field? Why does that magnetic field exert a force on the permanent magnet? The classical answer was given by James Clerk Maxwell in the 1860s in a set of equations that unified electricity and magnetism into a single theory. Maxwell's equations describe how electromagnetic fields propagate and interact. They are powerful, accurate, and widely used in engineering, but they do not explain what electromagnetism fundamentally is. They describe what it does. They do not explain why. The deep quantum answer was built by 3 physicists working independently in the late 1940s. Richard Feynman at Cornell University, Julian Schwinger at Harvard University, and Shinichiro Tominaga at Tokyo University of Education. Through different mathematical approaches, each one developed a complete quantum theory of how electromagnetic forces work at the most fundamental level. Their theory is called quantum electrodynamics. In the physics community, it is simply called QED. In 1965, Feynman, Schwinger, and Tominaga shared the Nobel Prize in Physics for this work. QED says this: every electromagnetic force, including the magnetic force that moves the coil in your earbud, is carried by virtual photons. A virtual photon is a photon that exists for only a very short moment. It is allowed to exist by Heisenberg's uncertainty principle, published in 1927. Heisenberg showed that the more precisely you know the energy of a quantum system at a given instant, the less precisely you can know the time involved, and vice versa. Virtual particles exploit this uncertainty. They borrow energy from the universe for a tiny sliver of time, carry electromagnetic force from one charged particle to another, and vanish before the books can be checked. The repulsion between 2 magnets, the push you feel when you try to press 2 north poles together, is being carried by virtual photons. The force that makes the earbud coil jump back and forth, and therefore the force that makes you hear music, is virtual photons in transit, billions of exchanges per second. QED predictions match experimental measurements to more than 10 decimal places. It is the most precisely tested theory in all of human knowledge. No experiment conducted in the 80 years since Feynman, Schwinger, and Tominaga published has contradicted it. The electromagnetic force running through the driver of your earbud has been described, verified, and confirmed with extraordinary precision. Every vibration of the diaphragm is a macroscopic consequence of a quantum mechanical foundation checked to 10 decimal places. Feynman once said that nobody really understands quantum mechanics, and that is the honest truth. Not in the intuitive way we understand why a ball rolls downhill or why a match produces fire. Quantum mechanics is a set of precise rules describing a reality that is fundamentally strange, but the rules work. Every time your earbud driver moves air against your eardrum, those rules are working exactly as predicted. Loud, invisible, quantum. Bring all 7 together. You are sitting in a noisy cafe, traffic outside, espresso machine hissing, conversation everywhere. You slip the earbuds in, you tap them to your phone, you turn on noise cancellation, you press play. Here's what happens in the first second. The flash memory chip loads your saved settings in microseconds. 65,000 configurations, each one a charge trapped in a floating gate accessed by electrons that quantum tunneled through a 10 nanometer glass wall. Fowler-Nordheim tunneling, described mathematically in 1928, running in your ear in 2025. The Bluetooth chip, built on transistors so small that quantum confinement shapes the energy levels available to every electron inside, receives the audio stream from your phone. The connection hops across 79 frequency channels at up to 1,600 hops per second. Each hop shifts the quantum energy of the photons carrying the signal. The chip tracks every hop. You hear nothing. The digital signal processor picks up the ambient cafe noise through the external microphone. It calculates the inverted wave. It fires the anti-noise through the driver before the original noise can reach your eardrum. The hum disappears. All of this in under 1 millisecond, on a chip designed using quantum mechanical models, running algorithms tuned in acoustic engineering labs, built from transistors sealed in hafnium oxide to keep quantum leakage from draining the battery before you finish your coffee. The lithium battery, its charging process now experimentally shown to involve quantum mechanical electron-ion coupling at the electrode interface, its solid electrolyte interface holding back tunneling electrons barrier by barrier, delivers steady power without interruption. The driver fires. Virtual photons exchange between the current electrons and the magnet electrons. Force transfers. The coil moves. The diaphragm moves. Air compresses and rarefies at frequencies from the lowest bass to the highest treble in the music. Sound enters your ear. You close your eyes. You hear music. There's nothing simple here. There never was. Now step back and think about what that century of discovery actually cost. The math that describes quantum tunneling runs to dozens of pages of differential equations. Erwin Schrödinger published his famous wave equation in 1926, building on Louis de Broglie's 1924 proposal that matter, not just light, has wave properties. Werner Heisenberg published his uncertainty principle in 1927. Niels Bohr and Albert Einstein argued for years about what quantum mechanics actually means, whether the wave function was real or just a mathematical tool. Einstein never fully accepted the strangeness. Bohr insisted the strangeness was the point. That argument is not fully resolved even today. What is resolved is that the equations work. The predictions match. The devices built on those predictions function. Your earbuds are one of the clearest demonstrations of this available to anyone in the world right now for less than the price of a dinner out. Think about the transistors inside the Bluetooth chip. The chip itself might be roughly 4 millimeters by 4 millimeters, smaller than a fingernail. Inside that area sit billions of transistors. Apple's H2 chip, used in AirPods Pro from 2022, was built on a 4 nanometer process and contains roughly 1 billion transistors, 1 billion switches, each one smaller than a virus, each one governed by quantum mechanics, each one switching on and off billions of times per second. The chip consumes roughly 1 milliwatt of power in active use, 1 milliwatt. That is about the power required to lift a single grain of rice 1 millimeter per second, running a billion quantum mechanical switches simultaneously. This is what quantum engineering looks like in a consumer product. The Bluetooth protocol itself was named after a Danish king. Harald Bluetooth Gormsen unified warring tribes in Denmark in the 10th century. In 1998, engineers at Ericsson, Nokia, Intel, Toshiba, and IBM named their new wireless communication standard after him, using his runic initials as the logo. The naming decision was made as a temporary placeholder that somehow stuck. What matters is the physics underneath the branding. The 2.4 gigahertz electromagnetic waves, the 79 channel frequency hopping, the packets of digital data encoded as waves and decoded by quantum designed chips. The frequency range Bluetooth uses, 2.4 gigahertz to 2.4835 gigahertz, is part of what is called the industrial, scientific, and medical frequency band. It is unlicensed, meaning any device can use it without paying the government for the privilege. Wi-Fi also uses this band. Microwave ovens also use this band. A microwave oven uses roughly 1,000 watts to heat food using 2.45 gigahertz radiation. Your Bluetooth earbud uses about 1 milliwatt to send music through the same frequency range. The difference is 6 orders of magnitude. The physics is the same. The engineering and the quantum management of that engineering is what separates them. Noise cancellation is worth pausing on a little longer. When people first hear about it, they often think the earbud is somehow blocking sound, building a wall against it. It is not. It is adding a sound, a very specific sound, an equal and opposite sound. The addition of these two sounds, the incoming noise and the generated anti-noise, produces a result of near zero, silence through addition. It runs against intuition so strongly that when the British engineer Harold Haas first proposed a related concept in acoustics, listeners needed time to accept it. The engineering challenge is timing. If the anti-noise arrives even half a millisecond too late, the cancellation is imperfect. The earbud microphone captures the incoming noise. The DSP chip needs to process the signal and generate the anti-noise in time to reach the ear canal before the original noise does. For low frequencies, bass rumbles, engine hums, HVAC noise, the waves are long. The wavelengths are measured in centimeters. The DSP has more time. For high frequencies, speech, sharp transient sounds, the waves are short and change rapidly. The DSP has almost no time. This is why noise cancellation is excellent against the constant drone of airplane engines and less effective against someone speaking directly to you. Modern feed-forward and feedback hybrid systems address this by using multiple microphones. An external microphone, called the feed-forward mic, catches noise before it enters the ear canal. An internal microphone, called the feedback mic, catches noise that has already entered the ear canal. The DSP uses both signals simultaneously, creating a more accurate and faster cancellation. The algorithms running this process are proprietary and tightly guarded. Qualcomm, Apple, Sony, and others spend enormous engineering effort refining them. But the underlying physics, destructive interference of sound waves, is the same principle Lueg wrote down in his 1933 patent. Look at the driver one more time. The diaphragm is the part you never see. It is a thin dome, typically made of polymer, paper, or aluminum alloy, depending on the manufacturer's tuning goals. Harder materials like aluminum respond faster to rapid frequency changes. Softer materials like polymer tend to produce a warmer sound. The diaphragm in a high-quality earbud might weigh less than half a milligram. Half a milligram is roughly the weight of a grain of flour. At 20,000 hertz, that half-milligram dome completes 20,000 complete back-and-forth cycles per second. It accelerates and decelerates at forces far exceeding anything a car experiences in a crash, many times per second, without braking. The tolerances and material engineering required to make this work reliably are enormous, even before the quantum physics of what drives the coil enters the picture. The permanent magnet in most earbuds today is made from neodymium iron boron, a rare earth magnet material discovered in 1982 simultaneously by General Motors and Sumitomo Special Metals. Neodymium magnets produce a much stronger magnetic field for their size than older magnets made of ferrite or alnico. A neodymium magnet the size of a pea can hold dozens of times more force than a ferrite magnet of the same size. This makes smaller, more powerful drivers possible. The quantum mechanical structure of neodymium iron boron, specifically the way the electron spins in the neodymium atom align under the right conditions, is what gives this material its extraordinary magnetic strength. Electron spin is another quantum property. It is not literally the electron spinning like a top. Spin is a quantum mechanical property with no classical equivalent. Electrons can have spin up or spin down, two states, no others, no intermediate values. When vast numbers of electron spins align in the same direction inside a material, the material becomes strongly magnetic. In neodymium iron boron, the crystal structure forces this alignment. The result is the strongest type of permanent magnet commercially available. The magnet in your earbud driver is strong because electron spin, a purely quantum mechanical quantity, is aligned by the crystalline geometry of the material. Every part of the earbud, looked at closely enough, runs on quantum mechanics. The memory stores data using quantum tunneling. The processor chip operates in a quantum confinement regime. The battery involves quantum mechanical electron transfer. The Bluetooth signal is carried by quantized photons. The noise cancellation uses wave mechanics to generate destructive interference. The driver magnet owes its strength to quantum mechanical electron spin. And the force that converts electrical current into mechanical motion is carried by virtual photons, as described by quantum electrodynamics, verified to 10 decimal places. None of this was designed with earbuds in mind. Fowler and Nordheim were studying field emission from metals. Feynman and Schwinger were trying to reconcile quantum mechanics with special relativity. Esaki was studying tunnel junctions for his own theoretical interest. The people who discovered the physics had no idea their equations would one day run inside a plastic shell smaller than a thumbnail, selling for less than a week's wages, in hundreds of millions of units per year. That is how physics works. The discovery comes first. The application follows, sometimes decades later, sometimes a century later. The equations wait patiently until engineers find a use for them, and then those equations run inside your ear, invisible, precise, and absolutely relentless. The NAND flash stores your music. The chip decodes it, the battery powers it, the Bluetooth delivers it, the DSP cancels the world around it, the driver plays it, the magnet drives the driver. All quantum mechanics, all happening right now. The electron did not ask permission, it still does not.